The ease of use, non-invasive nature, and low costs associated with pulse oximeters have resulted in their widespread use in diverse clinical settings. This lecture will focus on the application of oxygen saturation monitoring in critical emergency and disaster care settings.
My name is Keith Brock.
This lecture was supported by the UC Davis Point of Care Technology Center and the Point of Care Testing Center for Teaching and Research. At the conclusion of this lecture, students should be able to A. Interpret the basic engineering principles behind oxygen saturation measurement. B. Prepare the testing environment, patient, and pulse oximeter before testing. C. Demonstrate proper pulse oximeter testing techniques. And finally, D. Illustrate the proper pulse oximeter result processing considerations. Before we begin, I would like to introduce a few terms used throughout this lecture. Confounding factors are any variable which may mask an association or falsely demonstrate an apparent association, resulting in a biased test result. Dyshemoglobin is a hemoglobin form that is not capable of reversible physiochemical association with oxygen. Hemoglobin is the iron-containing red pigment protein of erythrocytes. Deoxyhemoglobin is deoxygenated hemoglobin, and oxyhemoglobin is oxygenated hemoglobin. Perfusion is presence of blood flow, and finally, point-of-care testing is testing at or near the site of patient care. Pulse oximetry uses the properties of absorption to non-invasively approximate arterial oxygen saturation. Different hemoglobin species absorb light at different wavelengths. At least 2 wavelengths of light are required to accurately measure oxygen saturation. Here we have illustrated the absorption spectra of oxygenated hemoglobin, shown as a red curve, and deoxygenated hemoglobin, shown as a green curve. The extinction coefficient is plotted against the wavelength of light. The deoxyhemoglobin curve in green is above the oxyhemoglobin curve in red through the red light spectrum because deoxyhemoglobin absorbs more red light. Increasing the wavelength into the infrared light spectrum, we find the oxyhemoglobin curve above the deoxyhemoglobin curve, indicating oxyhemoglobin's tendency to absorb more infrared than deoxyhemoglobin. Interrogating blood at these 2 wavelengths can give an estimate of arterial oxygen saturation. For pulse oximetry, such as the sensors you place on the forehead, earlobe, nose, or finger, red and infrared light passes into the tissue, some light is then absorbed, and the photodetector measures the transmitted light. Along the light path, light is absorbed and scattered by blood, bone, tissue, and fingernails. Once again, oxyhemoglobin will absorb more infrared light than red light, and deoxygenated hemoglobin will absorb more red light than infrared. Here we have illustrated a simplified light path through a cross-section of tissue. Red and infrared light pass through the tissue, bone, fingernails, and blood until it reaches the photodetector. So 2 questions naturally come up from here. 1, how can the pulse oximeter convert the measured light absorption to the concentration of oxyhemoglobin? And 2, how can the pulse oximeter distinguish between light absorbed by hemoglobin versus anything else along the light path of the transmitted light? To answer the first question, we turn to the Beer-Lambert law. The Beer-Lambert law states that the absorption of light is related to the properties of the material, the concentration of the material, and the distance the light travels. For pulse oximetry, the material of interest is oxygenated hemoglobin. The concentration of oxyhemoglobin is what we want to find out. And finally, the path length for fingertip pulse oximetry, for example, is through the fingernail, the tissues of the fingertip, blood vessels, all the way through to the surface of the photodetector. For clarity, the Beer-Lambert law has been applied to our simplified cross-section. The Beer-Lambert equation is shown to the top left. And remember, absorption, or A, is measured by the photodetector. The absorptivity constant, epsilon, is a property of the material, and the path length L is from the light source to the photodetector, all of which can be used to estimate C, or the concentration of oxyhemoglobin. So now we have an idea of how the pulse oximeter could calculate the concentration of oxyhemoglobin from the measured absorption. But the second question still remains. How can the pulse oximeter distinguish between the light absorbed by bone, skin, fingernails, tattoos, or even venous blood? To answer this question, we must take advantage of the pulsatile nature of arterial blood flow and split the absorption signal into two, a static or unchanging component and a dynamic or pulsatile component. A fixed or static amount of light is absorbed by tissue and non-pulsatile blood in the venules. The static absorption component is also referred to as the DC component. Here, the path length, LD, is equal to the light path between arterial pulsations. The changing or dynamic absorption component is created by the pulsation of oxygenated blood into the arterioles. The dynamic absorption component is also referred to as the AC component. Here, the path length LS is the distance a light must travel during the pulsation of arterial blood. Applying the concept of AC and DC absorption components to our cross-section, we see that during pulsations, the systole path length is larger than the diastole path length. Thinking back to the Beer-Lambert equation, what effect on absorption will increasing the path length have? Good. It'll increase the absorption. Additionally, with more blood filling the arterioles, the concentration of hemoglobin should also increase, further elevating the absorption measured by the photodetector. The pulsatile arterial component, or AC, is typically only about 0.5% to 5% of the total light absorbed along the light path length. This contributes to the pulse oximeter's dependence on highly perfused tissue and ultimately signal quality. The AC signal is normalized to the corresponding DC signal for a given wavelength, either red or infrared, and a RIR ratio is calculated. The absorption ratio is averaged over 3 to 10 seconds to help reduce errors due to motion effects, one confounding factor in pulse oximetry. This figure illustrates the AC and DC absorption components and their respective subcomponents. The AC component is enlarged to show details of the dynamic waveform, also known as the plethysmographic waveform. Note that the significant majority of light is absorbed by skin, bone, and tissue, followed by venous blood and non-pulsatile arterial blood. Pulse co-oximetry uses similar absorption-based principles, but uses more than two wavelengths of light to determine the concentration of hemoglobin derivatives and the total hemoglobin within the blood non-invasively. Co-oximeters' ability to distinguish and measure dyshemoglobins may help eliminate dyshemoglobin effects on SpO2 measurements. Here we have illustrated the absorption spectrum of oxyhemoglobin, deoxyhemoglobin, methemoglobin, and carboxyhemoglobin. The presence of additional hemoglobin will cause errors in the SpO2 readings of pulse oximeters. In contrast, laboratory oximeters use multiple wavelengths to measure functional oxygen saturation as well as dyshemoglobins. All pulse oximeter and pulse co-oximeters estimate functional oxygen saturation, or the percentage of oxyhemoglobin in blood, assuming there is no dyshemoglobin species. In contrast, multi-wavelength laboratory oximeters calculate fractional oxygen saturation, wherein dyshemoglobin contributes to the denominator or the total hemoglobin calculation. Many factors affect the calibration of pulse oximeters, including light source, pressure of sensor, and the light path length. Manufacturers used induced hypoxia studies to explore the relationship between the RIR ratio and the experimentally measured SpO2 values. A typical hypoxia study consists of over 200 blood draws measured by a laboratory oximeter from 10 to 12 subjects spanning over 70% to 100% oxygen saturation. This figure illustrates how volunteer oxygen saturation is systematically stepped down to 70% with a oxygen saturation blood draw for comparison to RIR ratio measured by the pulse oximeter at each interval. For example, at baseline, the volunteer will have blood drawn for measurement by the laboratory oximeter paired with an RIR ratio measured by the pulse oximeter. After stepping the volunteer's oxygen saturation down to 95%, a second pair of laboratory oximeter and pulse oximeter measurements are collected, and so on and so forth. Until the researchers can develop a calibration curve demonstrating the relationship between the lab oximeter oxygen saturation measurement on the y-axis to the RIR ratio measured by the pulse oximeter on the x. This calibration curve is programmed into each pulse oximeter and is how the meter converts the measured RIR ratio to the estimated oxygen saturation. Note, what happens when the patient's O2 saturation drops below 70%? This question highlights the inherent limitations of empirical calibration. For ethical reasons, manufacturers cannot induce severe hypoxia repeatedly in volunteers for calibration purposes. Manufacturers must rely on extrapolated SpO2 values for large RIR values, increasing the potential for error at low oxygen saturations. Additionally, the calibration of pulse oximeters is built in by the manufacturers and is not adjustable by users. Therefore, test operators are encouraged to ask manufacturers for supporting accuracy data and to consider manufacturer specifications prior to purchasing or using any pulse oximeter. In choosing a pulse oximeter, operators currently have many options to match their particular clinical environment. For instance, the fingertip transmission pulse oximeter was used in Thailand by disaster responders following the tsunami. Transmission pulse oximetry often has a larger AC or dynamic absorption component, equating to a stronger light signal. In contrast, surface or reflection pulse oximeters are designed to be placed on the patient's forehead, ear, nose, or in the case of neonates, the foot. Either sensor type can be equipped with multiple features such as printers and Bluetooth connectivity, or report additional measurements such as perfusion index, and in the case of pulse co-oximeters, such as the one shown in the bottom right, recent developments in the field have made it possible to estimate dyshemoglobin concentrations as well as continuous measurement of hemoglobin concentration. In surface pulse oximetry, the light source is adjacent to the photodetector and measures the backscatter of light rather than transmitted light. Orientation of light source and photodetector aside, the mechanism of detection in surface versus transmission pulse oximetry is identical. Despite the transmission style pulse oximeters often having a stronger signal, some studies have shown that the forehead is a better sensor site than fingers in tracking desaturation and resaturation events. This phenomenon is hypothesized to be caused by the proximity of forehead arterioles to the heart in the circulatory system. There are additional advantages to surface pulse oximeters, which we will cover as we explore additional pulse oximetry confounding factors. Now that we have a good understanding of the technology, let's explore this clinical utility and pre-analytical considerations for pulse oximetry. The purpose of pulse oximetry is to non-invasively measure the level of blood oxygenation. Pulse oximeters minimally display SpO2 as a percentage and pulse rate in beats per minute. The perfusion indicator reports the signal quality. Trend oxygen saturation data can be helpful between periods of direct arterial blood analysis when supported by mechanical ventilation or receiving respiratory depressants, and when arterial blood analysis would be impractical. Here we illustrate where each value is displayed on a typical fingertip pulse oximeter. Note that the signal quality indicator may be represented as a perfusion indicator, using colors to indicate signal quality, or in other models, signal quality may be displayed in the form of a perfusion index or a plethysmographic waveform. Pulse oximeters are currently used in various environments, including anywhere anesthetic is in use, such as on the way to, within, and returning from the operating room, emergency department, and intensive care unit. Because pulse oximeters are reagentless, they are especially environmentally robust, and can also be used outside the hospital setting in air, land, and sea medical transport, mobile hospitals, or alternate care facilities. Before using pulse oximeters, the patient or disaster victim should be assessed for potential interference, such as carbon monoxide poisoning, as this will likely interfere with the functional oxygen saturation approximation reported by the pulse oximeter. Many pulse oximeters are approved for use in adults and pediatric patients. Operators should always consult with the manufacturer operating specifications to look for the approved age, patient victim age, and weight. Transmission pulse oximeters will often require the sensor placement on patients' fingers, and not the thumbs, of a specific range and thickness. When selecting a sensor site location, consider the following. The sensor site should be well perfused, clean, dry, and should completely cover the sensor's photodetector. For fingertip pulse oximeters, index, middle, or ring fingers of the non-dominant hand is preferred. The big toe or adjacent toe may be substituted for a finger if necessary. The forehead is the preferred site for surface pulse oximeters, followed by the earlobe, then the nose. For approved use in neonates, the palm, toe, or lateral aspect of the foot are preferred. The sensor site extremities should be free of blood pressure cuffs or intravenous or intra-arterial catheters. And in the cases of poor perfusion, local rewarming may restore signal quality. The measurement duration and quality of signal are two major analytical considerations for pulse oximetry. During continuous use, periodically check for proper skin contact, tissue integrity, and perfusion. Poor signal quality may arise from inadequate arterial pulsations due to vasoconstriction, venous congestion, or low blood pressure. The quality of signal may also be compromised by high noise levels caused by patient motion, ambient light, or electronic interference. Again, the plasmographic waveform can be used as an indicator of signal quality as it should approximate the arterial blood pressure waveform. Most pulse oximeters will be equipped with a signal quality indicator that will prompt the operator of low signal quality. In emergencies and disasters, pulse oximetry can most readily be applied to victim triage, transportation, and inpatient care within an alternate care facility or a nearby hospital or clinic. The focus of any triage protocol is to rapidly separate victims into groups of varying injury severity. First responders must rapidly assess and track the vital signs, including oxygen saturation of victims. The victims will be addressed according to injury severity, vital sign stability, and responder resources. As victims are stabilized, transported off scene, or change in vital sign stability, so must the victim's designation of severity and allocation of resources. Continuous vital sign monitoring is preferred. Victims being transported from the disaster scene to a hospital, from one hospital to another, or within one hospital, can use pulse oximetry to continuously monitor the level of blood oxygenation to aid in the prevention of hypoxemia. During victim transport, the mode of transportation will depend on the resources available and the medical needs of the victim. Air transport should be reserved for the most critically injured victims, but special considerations should be addressed before moving a disaster victim by air. For this reason, SpO2 should be continually monitored during air transport. The Non-Invasive 2 is military airworthiness certified to function at 40,000 feet in an unpressurized cabin. Hospitals in the proximity of a disaster are often overwhelmed by victims arriving on their own or by land transportation from the disaster scene. Meanwhile, hospitals somewhat removed from the disaster remain underutilized. Fully connected diagnostic monitoring tests can create two-way information exchange between the ambulances and the healthcare facilities, dispersing victim impact on regional hospitals and clinics. Anytime a diagnostic or patient monitoring test is used outside the controlled environment of a hospital, the environmental limitations of the device should be well understood by the test operator. For patients transported by sea, this is absolutely critical. The Non-Invasive 2 is certified to operate at 0 to 40 degrees Celsius and at 10 to 90% humidity. Regardless of the mode of transportation selected, victim transport or evacuation following disaster will often require creativity and resourcefulness on the part of the first responders. Strategic positioning of point-of-care testing, including point-of-care SpO2 monitors in critical care infrastructure, creates a flexible and node-based small world network to address patient needs when resources are scarce. Adults and pediatric patients can be monitored using pulse oximetry in transit, at the community hospital and regional hospital in an emergency department, en route to the operating room, in the operating room, and during recovery on the wards. Here we illustrate one such small world network in rural Thailand. Following the temporal length from the community hospital in Ta Kato to the regional hospital in Kilasan, we find it would take approximately 2.2 hours to transport a victim. It quickly becomes apparent just how important neighboring resources become in a low-resource setting. The same can be said about mass casualty events here in the U.S. During a large-scale disaster or mass casualty event, or severe pandemic, regional hospitals will likely become overwhelmed. One way to increase surge capacity of the local medical system is to use alternate care facilities. Alternate care facilities can augment the regional community capacity temporarily to prevent emergency departments from becoming saturated with minor injuries or non-critical patients. Bluetooth-enabled pulse oximetry and other point-of-care devices with connectivity allow wireless transmission of victim data for decision-making. This illustrates an example of alternate care facility floor plan. Highly connected point-of-care bedside or near-patient testing should be integrated at multiple stages of patient care to maximize the disaster standard of care provided. The test operator should be familiar with troubleshooting recommendations from the specific pulse oximeter make and model being used. This table highlights some of the common problems, causes, and corrective actions for pulse oximeters. Low signal quality may be caused by inappropriate sensor position, poorly perfused site, dark skin pigmentation, or fingernail polish. Corrective actions include repositioning the sensor, rubbing the site vigorously for 20 to 30 seconds, selecting alternate sites, and always remove fingernail polish before performing pulse oximetry. Erratic oxygen saturation measurement is likely caused by patient motion or incorrect sensor position. Reposition the sensor to a site less prone to motion, such as the forehead, ear, or nose. If the pulse oximeter cannot detect a pulse, it cannot measure the oxygen saturation. This may be caused by the patient cable or sensor being defective or not connected. The sensor could be in an incorrect position, or the patient could be poorly perfused in the site selected. This also may be caused by tissue being too thick in the site selected, such as overly callous. To correct this, check the sensor connection or try a new cable. Reposition the sensor, and again, rub the site vigorously for 20 to 30 seconds to increase perfusion to the site. The functional oxygen saturation, or the non-invasive approximation of oxygen saturation, is an estimate of true oxyhemoglobin saturation and should be used in conjunction with other tests to fully assess hypoxia. Remember, pulse oximetry estimates how much the hemoglobin in arterial blood is saturated with oxygen, but cannot indicate whether an adequate amount of oxygen is reaching the vital organs or other tissues. Many pulse oximeters will have the capacity to record and store oxygen saturation, pulse rate, and associated data. Some meters are equipped with small printers that allow output of individual data prints or trend data over extended time periods. Pulse oximetry results should include the following: oxygen saturation values, inspired oxygen concentration and the delivery device, pulse rate, sensor site and signal quality, and the patient's position. In summary, the clinical utility of pulse oximetry is to non-invasively measure the level of blood oxygenation. Pulse oximeters display SpO2 as a percentage and pulse rate in beats per minute. Common uses include monitoring for ventilated patients, before, during, and following surgical procedures, hypoxemia screening, and vital sign monitoring. Variations of these functions take place in multiple clinical settings, including operating rooms, emergency departments, intensive care units, air, land, and sea medical transport, and alternate care facilities. Understanding the clinical limitations of pulse oximeters is critical to the proper use and result interpretation.
A thorough understanding of the multiple confounding factors common to pulse oximetry will help the operator troubleshoot strange or erratic measurements. Knowing the difference between functional and fractional oxygen saturation will prevent erroneous results due to the presence of dyshemoglobins. And lastly, being mindful that the reliability of pulse oximeters deteriorates in low saturation settings. The advantages of pulse oximetry are numerous, most notably the easy, non-invasive, instantaneous measurement of blood oxygenation and pulse rate with little to no risk of contamination. Pulse oximetry's continuous monitoring allows for critical trend data, and its environmental robustness to temperature, humidity, and altitude lend itself to multiple clinical settings.
Test the retention of information provided in this lecture by going through the following questions. Question 1. Describe the Beer-Lambert law and its application to pulse oximetry. Question 2. Based on current pulse oximetry calibration methods, why are pulse oximeters less reliable in low oxygen saturation levels? Question 3. What type of oxygen saturation do pulse oximeters measure, and why is this significant? Question 4. Describe the method by which manufacturers calibrate pulse oximeters. Question 5. Compare and contrast transmission and surface pulse oximeters. Question 6. Name 3 operator considerations when choosing a pulse oximeter sensor site. Question 7. How can pulse oximeter operators determine the signal quality? Question 8. How can the use of pulse oximetry aid in disaster care settings? Question 9. How would you troubleshoot an erratic SpO2 value? Question 10. Name the 5 results that should be recorded when managing pulse oximetry data. The following additional references are meant to give more in-depth information on pulse oximeter use and design. Thank you.